In this lesson, we will look for lines of symmetry. Figures that can be divided into mirror images by at least one line of symmetry are said to be reflective. If a mirror is placed on the line that you draw, the reflection in the mirror would look exactly the same. That is what reflective symmetry is. So if you have a regular triangle and a regular pentagon and need to find the number of lines of symmetry, I'm going to give you a few quick tips. The first is that you can connect a vertex, so a point, right through the middle. So on the triangle, that would be from the top right down through the bottom. If you folded that triangle right in half, that would be the same on both sides. Same thing with the pentagon. If I draw a line straight from the vertex down through the center, it's not perfect, sorry, there you go. If I folded on that line, it would look just the same. So that is one line of symmetry each. But there's another trick. We can also, with regular polygons, find lines of symmetry through each vertex. So that means on the triangle, because there are three vertices, there are 3 lines of symmetry. Here is an example. There is a line of symmetry. If I folded the triangle on the green line, it would also be the same. And there's one more going from this point through the center. So the triangle has 3 lines of symmetry. I bet you can guess how many the pentagon has. Pentagons have 5 vertices, and that means it has 5 lines of symmetry going through each vertex and crossing through the center. So far we have 2. There's line 3. Line 4 is the yellow line. And then finally, line 5 would go right through the middle. So the pentagon, because it has 5 vertices, has 5 lines of symmetry. When you have a regular quadrilateral or a regular hexagon, you have an even number of vertices, 4 for the quadrilateral and 6 for the hexagon. That means our lines of symmetry are just a little different, but the number is the same as with the triangle and the pentagon. For example, the square that we have here, this regular quadrilateral, has a line of symmetry going down the center vertically and also down the center horizontally. Let's see if I can move that. There we go. We also can draw lines through the vertex to the opposite vertex. So there's one going this direction and another one going diagonally. So in all, the quadrilateral, although it's split a little differently than the triangle and the pentagon, also has the same number of lines of symmetry as it does vertices. That means a hexagon should have 6 lines of symmetry, and we can prove it by drawing them. Just like the square, we're able to split the hexagon in halves that are reflective, shown by the blue, yellow, and green lines. But then we can also go through and connect the vertices. So far we have 3 lines of symmetry, and then if I connect the vertices, I'm going to add on an additional 1, 2, 3. So in all, I have 1, 2, 3, 4, 5, 6. I'm not going to count this again because I've already counted those lines. So indeed, the hexagon has 6 lines of reflective symmetry. Something new you may not have heard of is rotational symmetry. A figure has rotational symmetry if it is turned and retains the shape, which means it stays the same. It can't be turned all the way around. If you notice in this triangle, the A moves and ends up in the bottom corner. If the A had gone all the way back up to the top, we don't call that rotational symmetry because it means it's just going back to where it began. So it only has rotational symmetry if it turns less than a full turn but looks the same. So a triangle is a really good example. Can you tell which of these letters has rotational symmetry? If you saw that it's the H, you're right. If you notice, here's a capital letter H. If I start to turn it, it looks identical when it's been turned 180 degrees. It didn't have to go back to where it started to look the same. So H has rotational symmetry. The last type of symmetry that we'll talk about today is when there is a line of symmetry and something has been reflected over it. So it's almost like looking at the transformation known as a flip or reflection. Halfway between this figure and its reflection is a line of symmetry. In this case, there's a line of symmetry at the vertical line x equals 3. I will highlight where x equals 3 so that you can see what they're talking about. Here's the x-axis, so if we stop at 3, what they're saying is x equals 3, so this is where the line is. Can you see how this first shape is the same distance from that line of symmetry as this second shape? It's just been flipped. So this has reflective symmetry, and we would say it's been reflected over or across the line x equals 3. Does this shape have reflective symmetry? The answer is no. Notice how if the line of symmetry were x equals 3, the shape looks like it's just been slid over or moved rather than reflected. So this does not have a line of symmetry or reflective symmetry. This is not an example of that. In this lesson, you saw that you can find the lines of symmetry for regular polygons by counting the number of vertices that they have. For example, a pentagon has 5 vertices, so it has 5 lines of symmetry. You also learned about rotational symmetry, which means when a shape can be flipped around and look the same without going the entire 360 degrees back to where it started. You also learned about lines of symmetry and being reflected over a line of symmetry on a grid. These are 3 ways that we can talk about symmetry and explore symmetry in math.